Now, the structure of a neutron star resembles a bit the structure of a white dwarf, just that instead of having the pressure being given by electrons, you have the pressure being given by neutrons. But because it is not producing luminosity, you have the same structure. You have an isothermal interior. You have the atmosphere, which is a hot plasma, which is the zone where the temperature is changing. Under it, you have an outer crust, which is about 200-meter deep, which is fluid. You have the outer crust, and the inner crust is being still dominated by degenerate electrons. And in the outer core, then you have superfluid neutrons. You have a small number of superconducting protons, and the degenerate neutrons supply the main pressure. Now, in the inner core, it's uncertain. Matter here is very compressed. It's a very exotic state of matter. There may be a solid core consisting of elementary particles. The density here is approaching 10 to the 15 grams per cubic centimeter. It's denser than the density of the nuclei in an atomic nucleus. Now, what happens beyond that? Beyond the three solar masses, neutron degeneracy cannot hold gravity anymore. In the same way that you have the Chandrasekhar limit for white dwarfs, there is a limit also for the mass of neutron stars. As the highest mass that neutron degeneracy can still have to support gravity. And beyond that, no known force can hold gravity. The star implodes to a point of infinite density, and you have a black hole. Now, black holes are very simple compared to neutron stars. They are characterized completely by their mass, their charge, and their spin. The Schwarzschild radius is the radius beyond light cannot escape, is the radius of the event horizon. You simply equate the escape velocity with the light speed and have the expression for the Schwarzschild radius. So the event horizon is a sphere of radius equal to the event horizon. And here then we have a summary of stellar evolution. On the left-hand side, you have the mass, and here you have time. You have main sequence stars here. For low mass, main sequence stars become giants, undergo a helium flash, become HB stars, and go on to become planetary nebula. Higher mass stars become, from the main sequence, they burn helium in ideal gas. They do not undergo a helium flash. They undergo a supernova and leave either a neutron star or a black hole. So in the end, you have these compact objects that are the cemetery of stellar evolution: white dwarfs, neutron stars, and black holes. So you have in this way the chemical evolution of the galaxy, a chemical enrichment of the galaxy. You have hydrogen and helium, stars form from this hydrogen and helium. They burn their fuel and then eject their atmospheres back in the interstellar medium. But because of the products of nucleosynthesis, planetary nebulae and supernovae eject gas that are enriched in metals. So new stars are formed from this enriched gas, and this cycle continues. Essentially a recycling of matter that is increasing the metallicity of the galaxy. So this is a plot here that shows that indeed this idea makes sense. You have a metallicity gradient versus here the age of the stars and the metallicity gradient. You see, the older the stars are, the more metal poor they are, and the younger stars are more metal rich. There is clearly a gradient of metallicity with age. So the galaxy is increasing its metallicity as successive generations of stars enrich the ISM.